you, here we consider potentiometer is an instrument used for measuring EMFs, potential differences, and related to potential differences. Therefore, this instrument is called potentiometer. Basically, this potentiometer is a frame of wood on which 2 points, between those 2 points, uniform cross-section wire is folded and cut like this. So the length of this wire, one strip, will be of 1 meter length. So that between the connecting points A and B, we have 10 meters or 20 meters that we can define or we can design. So basically, this is what a potentiometer that you can see in the lab. Okay? Now, how we use this one to measure the EMF of a cell? Before that, we must know the principle of working of potentiometer. Principle of working. Is that when a steady current is allowed to flow through a wire of uniform area of cross section, potential drop across a length of the wire is always directly proportional to the length of the wire. Mathematically, potential drop, if I measure across a particular length, that potential difference V will be equal to I into R, where R is the resistance of that wire, I is the steady current flowing through it. Therefore, V will be equal to I into rho into L by V, where rho resistivity, L length of the wire, and A area of cross section of the wire. Now you can see steady current is allowed to flow through a wire of uniform area of cross section. That means these two things are constants. Resistivity is already a constant for the material under constant temperature, and therefore taking all these three together as a constant, we can say V directly proportional to L. This is what the principle behind the working of the potentiometer. Okay? Now, let us see how we are finding the EMF of a cell. This is not there in the syllabus, but you must know how it is used to determine the EMF of a cell. For that, we have to make a connection. See, that connection, when I draw, I am not drawing all these things there like cut and fold of the wire and all that. No. I will be taking the potentiometer symbolically. Okay? Now let this be the potentiometer wire. You can represent potentiometer like this. Length of the uniform cross section wire. And between points A and B, we make a common connection here. That is a cell, then a rheostat, and ammeter. This is what the connections. And this connection will be a common connection for all the potentiometer experiments. And this is called the primary connection or auxiliary, we can say. So here there will be a cell or a battery connected. Let that be B. Sorry, let us say the cell of EMF E1. B is already taken here, that is why. Rheostat, ammeter, key, and the wire. And this primary circuit is meant for sending a steady current through the potentiometer wire. Remember, to send a steady current through the potentiometer wire, this connection is made. That is why when all the experiments on potentiometer, the circuit remain constant. Now, I want to measure the EMF of a cell. That EMF E I am connecting over here, and a high resistance, I could say, high resistance, then a galvanometer and a job. Now the secondary part is like this. From the point A itself, EMF of the cell to be determined, that cell is connected, a high resistance and a galvanometer. Remember, this high resistance is to limit the current to this bar to protect the galvanometer from the high current. Okay. Now, when you make the connections, remember the positive terminals of both the cells are coming to this particular point. Both the cells positive must be coming here. Okay. Now, high resistance, how much it should be, that depends on the circuit and the current flowing through that. Sometimes it varies from 1 kilo ohm to 2 kilo ohm. That depends. That you can decide by connecting the circuit. Okay. Now, how to measure the EMF of the cell? For that, first of all, you have to check the connections whether it is okay. You will see, I close this bar so that this will be connected. And I set a current I flowing through this. Current will be flowing through this potentiometer. Now, I take the job key and press it close to A. I can see the deflection going on one side. And again, I take from there and put the job key at point B, close to B, the other end of the wire. You can see that the deflection is going to the other side. So if you are getting deflection on both the sides, we can say that the circuit is okay. Now after checking the circuit, we can start the experiment by fixing a current I here. And I move the jockey from A to B slowly. And as I move the jockey from A to B, the deflection on the galvanometer goes from left to right gradually. And the deflection goes from left to right gradually. And when it reaches at this particular point, galvanometer reads 0. And that particular point is called as your calling as balancing point. And this length of the wire we call it as balancing length L. That balances the EMF of this cell. So actually this cell is getting balanced across this length. After measuring this length, we can find the thickness of this wire using a screw gauge. From that you can find the area of cross section. And you got the current I flowing, area of cross section, balancing length we found, and material of the potentiometer wire, resistivity you can get it from the what you call log table. Knowing all these things, we can have the voltage V to be calculated as I into R or V equal to I into rho into L by E. And this particular current I is measured here. That is the current flowing through the potentiometer wire. Okay. Now, knowing all the values and using this equation, we can find the potential drop across this length of the wire. That is what we determine actually. This is the voltage drop across that particular length of the wire. Now, how this V is equal to E? That is what we are saying. This V is equal to E because I told you this length is balancing this EMF. Now, to understand that, let us consider only this part of the circuit. Only this much part. That is, this EMF is sending current through this, and here there is a potential drop because of the current I flowing through this one. And when this length of the wire, when we consider that length of the wire produces an EMF there or a drop there, that drop will be assumed as a voltage like this. That this voltage and this voltage, when it is equal, then no current flows through this path. That means this particular length of the wire provides a potential difference V. That V, when it is equal to this E, we get the galvanometer reading 0. And therefore, we can say V equal to E. This is what, or this is how we are finding the EMF of a cell. Okay?